Welcome to this talk about the better than true approximation for weighted tree augmentation. My name is Vera Traub and I will present some joint work together with Rico Zenklusen. Let me start by introducing the weighted tree augmentation problem. In this problem, we are given a tree G with vertices and edges, for example, the tree that you can see here in black in the left picture. And then we are also given an additional set of edges. These are the dashed orange edges, and we will call these XY edges the links in order to distinguish them from the edges of our tree G. These links come together with non-negative weights that are given by this weight function W here. Now, our goal in weighted tree augmentation is to find the minimal weight subset of the links that we can add to our tree G to make it tree edge connected. So as an example, those 4 orange links here in the picture on the left would form a feasible solution because if we add those to the tree G, we obtain a tree edge connected graph. Note that, well, it might seem a bit restrictive that we assume the graph G that we are starting with to be a tree, but in fact, it turns out that we could just as well start with any arbitrary connected graph G here, and the assumption that G is really a tree is actually without loss of generality, and that's just because of the fact that we can always contract to its connected components of the graph G up front, and thus we obtain without loss of generality a tree here. Now, in this talk, we want to discuss approximation algorithms for weighted tree augmentation. And for this purpose, it will be useful to view the weighted tree augmentation problem from a slightly different perspective. Let me to view it as a covering problem. What do I mean by this? So we call that our goal in weighted tree augmentation is to obtain a tree edge connected graph. So this means we want to make sure that every cut contains at least 2 edges. So this means the cuts we really care about are those cuts of the tree G that just contain a single edge of the tree. And so in other words, weighted tree augmentation is about covering the 1 cuts of the tree G, so which correspond to the edges of the tree G by links, where a link just covers the edges on the path PL between its endpoints. So we can now equivalently describe weighted tree augmentation as the problem of finding a minimum weight subset of the links that covers all the edges of the tree G, where a link just covers again the edges on the path PL between its endpoints. That's the problem definition. As the title of this talk suggests, our goal in this talk will be to obtain better than true approximations for this problem. But as a warm-up, let us start with a simple way of how we can obtain a true approximation. So this true approximation algorithm starts by picking an arbitrary root vertex R of our tree G. And then in the second step, we split every link in our instance into 2 so-called uplinks that each have the same weight as the original link. So what is an uplink? An uplink is simply a link where one endpoint of the link is an ancestor of the other endpoint of the link in the tree G. So all the links in this right picture here are uplinks. It turns out that it's always possible to split a link into 2 uplinks in such a way that those 2 uplinks cover precisely the same edges that were also covered by our original link. And so by doing the splitting operation, and clearly the weight of an optimum solution can increase by at most a factor 2. Now, why have we done that splitting operation? So that's because it's well known that if our instance now has only uplinks, it's possible to solve that instance optimally in polynomial time. There are various ways of doing this. One way would be to solve natural linear programming relaxation. This is integral in the special case where we only have uplinks. Another way would be to use a dynamic program bottom-up over the tree. But in any case, that gives us a simple true approximation for the weighted tree augmentation problem. So how can we do better? So this is known in several important special cases. So in particular, the unweighted tree augmentation problem, where all links have the same weight, has been heavily studied. The currently best known approximation ratio for that special case is 1.393, which we recently obtained in a joint work together with Rico and Rico Zenklusen, but that built up on some long line of earlier research. And then there are several other cases where better than true approximations were known. Now, let me just highlight one particularly important result here for this talk. This is a result by Cohen and Nutov, who gave a 1 + ln 2 approximation algorithm for the special case of constant diameter trees. And this is going to be particularly important for this talk because the algorithm that I want to present you later in this talk can be seen as a generalization of this algorithm by Cohen and Nutev to general instances of weighted tree augmentation. So now for the general weighted tree augmentation problem, a true approximation algorithm was for a long time the best we knew, and such a true approximation has first been obtained by Frederiksen and Jaeger about 40 years ago. And now the result I want to talk about today is the first improvement on this result by Frederiksen and Jaeger. Namely, I will talk about a polynomial time algorithm for weighted tree augmentation with approximation ratio 1 plus ln 2 plus epsilon, which is a bit less than 1.7. Okay, so in the rest of the talk, I want to explain to you how that algorithm works and give you a rough idea of how the analysis works. So our algorithm is the so-called relative greedy algorithm. Relative greedy algorithms have also been applied in several other different contexts. One prominent example is the relative greedy algorithm by Zenklusen for the standard tree problem, but another example would be, for example, this algorithm for constant diameter weighted tree augmentation by Cohen and Nutev. What's the general idea of a relative greedy algorithm? So the idea is just we start with some rather weak approximate solution, but that rather weak approximate solution should somehow be highly structured. And then in the course of the algorithm, we improve our solution, our starting solution, by replacing parts of this structured but weak starting solution by better components. So let's make that concrete for weighted tree augmentation. What's the starting solution for our algorithm? So the first thing we do is to obtain the starting solution as we apply that simple two approximation that I explained to you in the beginning of the talk. And then we, having this two approximate solution that contains only uplinks, want to make the solution even more structured. Namely, we want to make sure that every edge of our tree is covered not only by at least one of the uplinks, but it should be covered by exactly one of the uplinks in our true approximation U. So, for example, here in this picture here on the left, you can see this brown edge here is covered by two of the uplinks, namely by those two green ones. And in order to make sure that this brown edge is covered only by exactly one of the uplinks, what we do is we shorten one of those two green links, meaning basically moving one endpoint along that brown edge such that we end up with a picture like here on the right. And now the brown edge is covered by only one of the two uplinks. And it turns out that you can always do such shortening operations, and at the end you get an uplink solution where every edge is covered by precisely one of the uplinks. We just remark these shortening operations are always allowed or feasible because basically we just weaken the link. By shortening it, we just kind of pretend that the link covers less than what it actually does. So that's the starting solution for our relative greedy algorithm. And then now we want to improve on that starting solution. And that's what the actual relative greedy algorithm does. In this relative greedy algorithm, we will always maintain a feasible solution to our weighted tree augmentation problem that I will write as U union F, where U will always contain only uplinks and F can contain arbitrary links. Initially, we set U to be the starting solution, which was this two approximation, which consists only of uplinks and where every edge is covered just only by exactly one of the uplinks in the set U, and F is initially empty. So starting with the starting solution, we now want to make progress and make our solution cheaper. So what we do, as long as the weight of our solution decreases, so as long as we make progress, is we first select the component C. Think of a component just as of some subset of the links, for example, those two green links here in the picture. And then we add this component to our solution. This component can contain arbitrary links, not necessarily uplinks, and thus we add C to the set F. Now, if we add our component, some other links, like these two red links here in the picture, become redundant, and so now we would like to remove those links. And so the links we remove are those that are contained in the set drop of the component. And so this drop set consists of all the links in all the uplinks in U that cover only edges of the tree that are also covered by our component C. So these are uplinks in U that clearly become redundant once we add the component C. So those will be removed from our solution. And then we just iterate this process of repeatedly selecting a component, adding it, and removing redundant uplinks from U as long as we as the weight of our solution decreases. And then in the end, we just return the solution that we currently have. That's the algorithm. The only thing I haven't specified here is how do we select this component C. And what we do is we choose our component among some restricted class of possible components that I'll define in a minute or so. And among this restricted class of components, I pick C in such a way that it minimizes the ratio between the weight of the component, so the weight of what I add to my solution, and the weight of the drop, so the weight of what I remove from the solution. And so that's the choice of the component. And the important thing here is, of course, the important question is, what's that restricted class of possible components that I allow my algorithm to pick? And before telling you how we choose this class of components, let's think a little bit about what kind of properties that class of components should have. The first thing that we clearly need is that we should be able to efficiently find a component minimizing this ratio here. Otherwise, we can't even implement our algorithm in polynomial time. Once we have that, we can implement the algorithm. But now the question is, what do we need in order to make sure that the approximation ratio is good? So for this, we need a second property. And basically what we need to show is that at least initially, once the weight of our solution in U is still very large, where U is only a true approximation, we should be able to make some progress. And that's why we need that second property here that tells it, that basically says, if the weight of U is still much more than the weight of opt, there should exist some component that we can use to make progress. So the ratio here between the weight of what I add and the weight of what I can remove is significantly less than 1. So this ratio here should be bounded away from 1. Once one has this property B here, it's not hard to show that the relative greedy algorithm has an approximation ratio of better than 2. Because that basically guarantees us that as long as we haven't yet replaced a large fraction of U by some better component, or maybe if U is already better than 2 approximation at the beginning, we're anyways happy, then we will always find a component where we can make things sort of significantly cheaper. Okay, now how do we choose the components now in the end? So one very natural choice for this class of components would be to allow all constant size link sets. That's what Cole and Newton updated in their algorithm for constant diameter trees. The nice thing about this is then property A is trivial. We can just find the best component by enumerating over all of them. Unfortunately, for general weighted tree augmentation, property B does not hold. And there is an example that shows that if you just allow constant size link sets as components, relative greedy algorithm does not have an approximation ratio better than 2. So we give an example for this in our paper. Another sort of natural choice at the other end of the spectrum would be just, what if we just allow all arbitrary link sets as components? The nice thing is then property B becomes trivial because we can always just choose as a component the optimal solution. Unfortunately, it's very unclear how we should then efficiently find the best component to pick next, and most likely that's impossible in polynomial time. So now the question is, does there exist some class of components sort of in between here that fulfills both A and B? The class of component should be large enough such that it always contains a good component that we can use to make progress whenever we need it. But on the other hand, that class of component should be structured enough such that we are able to efficiently find the best component to pick next in our algorithm. And such a class of component indeed exists, and that's what we call the K-thin link sets. So let me show you the definition of this. So we call a subset of the links K-thin if for every vertex in our tree, there are at most K links for which the vertex V lies on the path PL between the endpoints of the link. So here is an example on the right. I claim that those 3 orange links here form a too thin component. So in order to, let's go through the definition together. So in order to check that this is indeed too thin, we need to look at every vertex V here in our tree, for example, that blue one here, and then we need to look at all these green paths here between the endpoints of a link. So here's the one green path for this thick link here. If you look at the first path, V lies on that path. second green path, V again lies on that path, and the third green path, V does not lie on the path, so V lies on at most two of these paths between the endpoints of links in our component. And you can check that this condition also holds for any other vertex V in this tree, and this is why we call the component consisting of these three orange links too thin. Now, why are these k-thin components good? First of all, we need this property A here, that we can efficiently find the best component to choose next. And it turns out that this can be done using some dynamic program going bottom up over the tree. And in fact, and sometimes this definition of k-thinness is made up in such a way that this dynamic program going bottom up over the tree has polynomial runtime for constant k. So that's property A. The more interesting part is property B. So why is it true that as long as the weight of U is much larger than the weight of up, there always exists a good component that we can use to make progress in our algorithm? And in order to show this property B here, we prove a new theorem, which we call the decomposition theorem, which is sort of the main technical tool that we need in order to analyze our algorithm. And that's where sort of most of the work in the analysis goes into. So let me show you that decomposition theorem, which is the key part of our analysis. The setting is the following. So we have some constant epsilon, some positive epsilon, which will later appear in our approximation ratio. And then we have that set U, which is the set of uplinks that when any two uplinks never cover the same edge. And then here's a statement of the decomposition theorem. So the decomposition theorem says the following. There exists a partition of the optimal solution into 1 over epsilon thin components such that we can lower bound the weights of these drops of these components, the total summing up of all components, by this expression here. And let's think a little bit about why this is a good lower bound. So suppose we somehow partition opt into several components. What's the best thing that we could hope for in general? Well, that's sort of that. The best thing we could hope for in general is that every single uplink in U is part of one of the drop sets of these components. And that's the best thing we could hope for in general. And in that case, we could lower bound the sum of the weights of the drops here by the weight of U. And this decomposition theorem tells us we can almost achieve that best bound that we could possibly hope for. We only lose that arbitrary, there's 1 minus epsilon factor here, which is arbitrarily close to 1. So basically, yeah, we can get as close as we want to this best possible bound. Once one have this decomposition theorem, it's actually easy to show the existence of improving components just by some simple averaging argument over the components in C. Basically, we know that summing up over all the components, the total weight is just the weight of opt because they form a partition of opt. So in total, these components are cheap. And we also know that the sum of the drops is large. So this, by an averaging argument, shows there must be one component where the weight of the component is relatively small compared to the weight of its drop. And that guarantees the existence of improving components. The main part of the work is really proving this decomposition theorem here. Okay, but in the interest of time, I won't talk about the proof of this decomposition theorem, and I will already conclude with a brief summary. So what I've shown you in this talk is the first improvement on this long-standing approximation ratio of 2 for weighted tree augmentation. We do this by giving an algorithm for weighted tree augmentation with approximation ratio 1 plus ln 2 plus epsilon, which is slightly less than 1.7. And then let me remark that in some recent follow-up work, which appeared at SODA this year, we could show that there is even a 3/2 plus epsilon approximation algorithm for weighted tree augmentation that's improving our approximation ratio that I was talking about here today. And then let me conclude with 2 open questions. Namely, the first one is, can we beat the factor 2 for weighted connectivity augmentation? So weighted connectivity augmentation is a generalization of weighted tree augmentation, which is basically about increasing the edge connectivity of a given graph from k to k plus 1 in the cheapest possible way. And currently the best known approximation ratio is 2. And then the second question is, can we beat the factor 2 for the minimum weight 2-edge connected spanning subgraph problem? Again, this is also an interesting generalization of where the true augmentation, where currently the best known approximation factor is 2. And with these 2 open questions, I would like to conclude my talk. So thanks for listening.